yeah. Ooh, that's why I'm easy. I'm easy like Sunday morning. That's why I'm easy. I'm easy like Sunday morning.
Hello everybody, Dr. Alex Vasquez coming to you live to talk about a very important nutrient, and the way that I'm going to introduce this nutrient, at least right now, to make it more mysterious, is to ask you the question. Let me just think about the question before I actually ask it. I think this would be, I'm trying to merge two questions together. So basically the question would be, what vitamin has the most complicated absorption? I have to think about all the vitamins when I ask that question, because then I want to make sure that my own question is correct. So what vitamin has the most complicated absorption? And that same vitamin, when deficient, the deficiency of that vitamin leads to permanent brain damage. So those are the ways I'm going to introduce this topic. If you've studied nutrition, then I think the answer to those questions, because obviously I'm looking for the same answer to both of those questions. So which vitamin has the most complicated absorption, and deficiency of that same vitamin can cause permanent brain damage? I mean, there's based on those two questions, only one answer exists. Although, arguably, we could find some other nutrients that have complicated absorption, but nothing is as complicated as the one that I'm looking for, the answer I'm looking for. And arguably, deficiency of several different nutrients could cause permanent brain damage, like B6, for example, even vitamin E, lipoic acid, CoQ10, but the advantage to lipoic acid and CoQ10, of course, is that they are produced endogenously. So absolute deficiency to the point of death is actually pretty rare. But with the nutrient that I'm thinking of, deficiency of that particular nutrient, which cannot be produced endogenously, has to be acquired from the diet. And if it's not acquired from the diet, because of its complex absorption and metabolism, then that can lead to permanent brain damage and, of course, eventually death. So some of you know exactly what I'm talking about, and some of you don't. So if you don't know the answer by now, you're not going to know what it is. But I'll tell you the correct answer that I'm looking for is vitamin B12. So what I'm going to do right now is go through the pharmacology of vitamin B12. I've been thinking about this for, let's just say, a week, maybe 5 days. Not for any particular reason, except for one particular reason. And that is because I think I know someone who has this condition. And so because of that, this topic has been on my mind. So that's it. So let's just dive into it. My initial plan was just to talk about this kind of generally, and then look at some research articles that I've obviously collected over the past 20 years, and which I've somewhat refreshed and organized over the last 2 days. But it's a massive amount of research and case reports and editorials and case series and things like that. So I was looking at it again yesterday, and it's just such a massive amount of information that what I think I'll do is I'll start the topic today, and I'm telling you ahead of time, today's conversation will be sufficient. So everything that we need to know about this topic, I'm about to talk about right now. But I think maybe I will do a review of the research articles, and I'll just go through the articles and point out what's interesting, Uh, like I said, it could be 100 articles, it could be 200 articles. I haven't counted them because I just started opening documents, and I was thinking that maybe it was 50 documents or something like that, but now I think it could be 150. And for that reason, the review of those articles is going to require its own video, assuming that I do it. I don't really think it's necessary, but I already started organizing them and looking at them, and some of them are quite interesting. So this will either be a video series of 2 parts, the introduction right now, and then I'll do a more polished version, or it'll be a video series of 3 parts, this introduction, then the literature review, and then I'll clean it up and make something more solid into a publishable document or a presentable document. But right now what I'm going to do is just start talking about vitamin B12. And I'll use the pharmacology acronym that I've already developed for vitamin D because that's the most obvious way to present this in an organized manner. So I'm just going to start writing, and here we go. So the structure to the conversation, again, the topic being the pharmacology of vitamin B12, the structure is going to be the FACILE acronym that I introduced now over the course of the past couple of months. So it's FACILE. So the F stands for function. You have to know something about the nutrient or the drug. So I call that function. And after function, we go to what was initially application, but what I prefer to call as administration. If we call it administration, then that kind of takes us into a specific cluster of 4 items that we discuss in the study of pharmacology, and that is administration, distribution, metabolism, and excretion. So I think I'll use that model. After the A, we go to C, which, as I recall, would be cautions. So, in medicine, including nutritional medicine and botanical medicine, not simply pharmaceutical medicine, we always have to think about what's the caution or what's the risk. Like I said, without trying to be too disparaging, anybody can walk into a pharmacy or a vitamin store and take something off the shelf and start taking it. So, the administration is actually the easiest part. But the perhaps we could say the true knowledge comes to the fore when we're aware of the cautions. So as I recall from my own acronym, I think the C stands for cautions. I stands for interactions. And I've liked that for I guess now 15 years or so. I like to think in terms of interactions with drugs and diseases. So it's another way, it's kind of a secondary way of looking at the C, which is caution, to look at I. It's another way of asking yourself the same question basically, but from a different perspective. To see if the patient in front of you or the person in front of you has any additional risk factors that you haven't quite thought of, or you didn't think of it the right way the first time, but to look for interactions with drugs and diseases. It works for me. I like it. The L stands for laboratory. Do you need to do any laboratory testing before you do this or while you're doing it? For example, some nutrients, mostly iron is the best example. We really need to administer iron based on laboratory testing. I've talked about that before in some other blog posts and articles and book chapters and things like that. Iron was, as some of you know, my first topic. When I first started doing, legitimate literature reviews and writing and publishing and things like that, iron was my first topic. I published my first article in the school newspaper And then second to that was the Townsend Letter for Doctors. And then a nutritional journal published by an organization within the American Chiropractic Association. I published a big monograph there. And then, so that was in 1994. And then in 1996, I published a letter to the editor in Arthritis and Rheumatism, which is the official journal of the American College of Rheumatology. So, I kind of built my expertise appropriately in kind of a stepwise fashion. But again, going back to laboratory testing, iron is a really good example of a nutrient that requires laboratory testing. I suppose it could be the only nutrient that clearly requires laboratory testing. So we'll talk about laboratory testing, and then the E at the end is explanation. So, if we're prescribing an antibiotic or something like that, we have to explain to the patient, the risks and benefits of the antibiotic, alternatives, if any exist. Sometimes they do. Like, for example, if you're treating small intestine bacterial overgrowth, you can use rifaximin, of course, if you want to spend $2,000 a month or $2,000 a week or whatever. It used to be really expensive. I assume it still is. But you could accomplish most of the same with berberine, for that matter. So, let's say a patient comes in and they've seen an article about rifaximin. I could say, yeah, we can do that. But we could also be cheaper and probably more effective using an alternative, which is berberine. So I happen to have gone at the time to a really good chiropractic college. And the way that we learned to document the process of informed consent was PARB. Like you could write it just PARB, or you could write it PAR-B, or you could write it PARB questions answered. That's the way that we learned to do it, which was much better than anything we learned in medical school or hospital training. But the PAR stands for Procedures, Alternatives, and Risks. Procedures, alternatives, risks. Obviously, you would have already explained the benefits. And then you would say questions answered. So if we were taught to document that in the charts, just to make sure we had provided good, clean, informed consent. Right now, after the whole plandemic that we've been through for the past 5 years, informed consent is part of medical ethics. And obviously medical ethics was completely destroyed for the implementation of the plandemic over the past 5 years. So when I talk about informed consent, I'm kind of showing that I come from a previous generation, not the globalist generation. All right, so diving into this topic, let's go with, I'm just going to write out, so I'm going to write this out in kind of an academic format. But let's see if I can get it all done, maybe even on one page. So I'll go F, function, A for administration, again, it could have been application, but I think administration is better, because when I think of administration from a pharmacology standpoint, then I go to distribution, metabolism, and excretion. So we're function, administration, cautions. We do have some cautions with B12. Even though I personally give it out and eat it like candy, we do have a little bit of caution. I'll tell you about that in just a moment. It's a caution or a pseudo-caution. I'll distinguish those in just a moment. Function, administration, course, FACILE, interactions. Lab. I'm gonna trick you all on the labs, because some of you think you're experts in B12, and maybe some of you are, but some of you are not. function, administration, cautions, interactions, lab, and then explanation. Again, strictly speaking, that would be procedures, alternatives, risks, and benefits with questions answered. Or you could do questions answered. So let's see if I can fit this whole conversation, FACILE, into this template, so to speak. Let me see. I'm going to change my color of ink here just to make it stand out a little bit differently. Maybe that's the wrong color. But anyway, that's what I've got. Let's see. So the function of B12 is actually pretty interesting because we can use B12 physiologically or we can use B12 pharmacologically. And I'll tell you what I mean. First of all, if we're going to talk about B12, we would have to talk about what is B12. B12 is it's obviously a vitamin. It's one of the B vitamins. Generally speaking, most of the time, not always, but most B vitamins are cofactors for enzymes, and that is they make enzymes work better. So your body creates an enzyme. All enzymes are proteins, and usually they're globular proteins. So let's just say the enzyme looks like this, and its job is to do something, to change the shape of a protein or add a group to another protein or something like that. I'm just looking for a model. I don't really have a good model in front of me. And maybe I don't need a model. But anyway, let's just say that it's a globular protein. Enzymes are typically globular proteins. And they change the shape of things or they add a group onto something else. All right, I'll use an example. So this is just a hydrocortisone cream that I use for bug bites. So let's say that this is another protein and this is an enzyme. Well, perhaps the function of this enzyme is to change the shape of this protein. So let's just say, but again, like I'm introducing, B vitamins are typically cofactors for enzymes, and what that means is that it helps the enzyme to work better. The enzyme may or may not be able to work without its cofactor. That's why vitamins are important for life. But again, this globular protein called an enzyme is going to work better if it has its cofactor. In this case, we're talking about B12. We could be talking about folic acid or B6 or thiamine or riboflavin or niacin. But let's say, I'll give you two examples. Let's just say this is a globular protein. It needs to have, I actually have a great model for this if I happen to have it in front of me, which I probably don't. Okay, well, let's just go with this. Let's assume that this is the vitamin. I would prefer that it be just a key chain instead of the key itself, but whatever. Let's just say this is a lot of times when we talk about vitamins, we talk about a lock and key theory, so anyway, it's somewhat accurate. Let's assume that this is the protein, the globular protein. It wants to do something to the other protein that we're about to manipulate. And let's say that this is the vitamin. And the vitamin has to hook on to the globular protein in some way. I'm just using a key ring because it's the only thing I found. I was trying to use one of my wedding rings, but I couldn't find it. It's in a different place. So you've got a globular protein. You've got an enzyme cofactor. Now this thing's ready to go. It encounters its substrate, which is the thing it's going to act on. And now that this protein is activated with its cofactor, it's either going to bend the protein or detach a phosphate group or some type of other group, or add a group back onto this protein. So that's what metabolism is. Metabolism is changing things. We change from one to another. We change the shape. We put active groups on. We take active groups off. Whatever. It could be a mineral. So let's say this is a protein. Let's say this is another enzyme, and we want to activate that enzyme. So we want to phosphorylate it by adding a phosphate group. And so we're going to add a phosphate group, but we need an enzyme to do that. And so this could be an enzyme that requires a vitamin. And this this enzyme may also require ATP from mitochondrial production, for example. So again, all of the B vitamins, I think except for one, function as cofactors. And a cofactor is, so the function is, I'll just say cofactor. Oops. The function, it's obviously a cofactor. Well, that's not obvious. It is a cofactor. When that's its physiologic role. The physiologic role of vitamin B12 is to function as a cofactor. However, we can also use vitamin B12 as a binding agent or a chelating agent. I'm going to say binding. And that would be its pharmacological role. Pharmacology. So if we were working in an emergency room or emergency department of some hospital, we could and we should have vitamin B12 available to use as a binding agent in case of certain types of poisoning. So vitamin B12 is unique. First of all, it's a huge molecule. It's a huge complex molecule that has cobalt in the middle of the ring. So the molecule of vitamin B12 has like a big circle, almost kind of like a head, you could say, and then it has kind of a tail structure to it. But within the center of that circle is a mineral called cobalt. That's why the chemical name for vitamin B12 is cobalamin or cobalamin. It's an amino acid, so it's an amine, or at least it was initially thought of as being a vital amine. That's where vitamin comes from. So it was described as an amine with cobalt. So that's why it's called cobalamin, because it has cobalt in the middle of this ring. So the complexity of its structure allows it to bind onto things. And what it binds onto specifically is cyanide, as in ant poison and rat poison. Vitamin B12 binds onto cyanide, and it also binds onto hydrogen sulfide, which is H2S. Hydrogen sulfide, for example, you produce it in your body all the time. You produce it within your body, you also produce it within your gastrointestinal tract. And it's also a product of sewage treatment plants and other chemical processes, in which case it can be produced in excess, and people can be exposed to it and they can die from it. And they do die from it, just like they die with cyanide. But one of the emergency room remedies or treatments for cyanide poisoning is vitamin B12. Likewise with hydrogen sulfide, vitamin B12 is one of the best treatments. So whether you want to call it, you can call it what you want. Probably B12, even at physiologic levels, functions to bind cyanide and hydrogen sulfide, even at physiologic levels. But pharmacologically, the respected use for vitamin B12 is the emergency poisoning treatment, the binding of cyanide and or the binding of hydrogen sulfide. So, going back to the physiologic roles, we know that B12 is necessary for kind of DNA function, so to speak. That includes methylation. So methylation is kind of a process of covering and uncovering certain genes so they are either expressed or they're not expressed. We know that it's important for blood formation. Everybody should know that. It's also important for mitochondria. I guess I'll come down here. It's also important for mitochondria. and it's also important for creating the myelin sheath around your nerves and also within the brain. So in your peripheral nerves, the nerves in your body, the myelin is created by a group of cells called Schwann cells, and they just wrap their bodies, so to speak, around the nerves, and that kind of protects the nerves and makes them work better. In the central nervous system, the distinction is that the myelin sheath is created by oligodendrocytes, and they don't really wrap their bodies around the cells as much as they wrap kind of appendages and processes. So one of the histologic distinctions between the peripheral nervous system and the central nervous system is the peripheral nervous system has a myelin sheath of Schwann cells, and the central nervous system uses oligodendrocytes. So back to talking about the function. Before you can even know the function, you have to know the structure. And in this case, vitamin B12 exists in 4 different structures. These are cyanocobalamin, cyanohydroxycobalamin, adenosylcobalamin, and methylcobalamin. So, as those names imply, we're still using the same base of cobalamin, but we're just adding different groups onto it. It could be a cyanide group, which is kind of a paradox because, yes, cyanocobalamin contains clinically significant amounts of cyanide. So, you have to know which form to use in which patient. You obviously, and this was brilliantly discussed about 40 years ago, I think in the Journal of the Royal Society of Medicine, an organization out of London, which I used to be a member there. So you obviously wouldn't give cyanide, you obviously wouldn't give cyanocobalamin, the form of B12 that has cyanide, you wouldn't give cyanocobalamin to somebody who already has cyanide poisoning. For example, chronic smokers, for example. That's the classic example. Hydroxycobalamin, I like it a lot. It's one of my preferred forms, and it's the better binding agent for hydrogen sulfide and for cyanide. So when I think of using B12 as a binding agent for either cyanide or hydrogen sulfide, I use hydroxycobalamin. Adenosylcobalamin, I tend to think of that as being more specific to mitochondria. So if I'm working with somebody who has some type of mitochondrial disorder, if I have to choose one or the other, yeah, I'll go with adenosylcobalamin.
Yeah, ooh, that's why I'm easy.